So please, take it away. Really looking forward to hearing about your work on wastewater.
Great, thank you. Wonderful to be here today. Let me set up my screen. All right, how does this look? Everyone is, where did you go? All right, sorry, just moving so I can see those of you with your cameras on. All right, the screen looks good. Perfect. All right, so today I'm going to be presenting kind of an overview of methane emissions from wastewater and include some work that I've done while at LBL, sort of modeling nationwide greenhouse gas emissions from the sector. But because this is a meta talk and I know it tends to skew heavily towards oil and gas, I wanted to start by just giving you like an overview of where are we seeing methane emissions coming from wastewater and touching a little bit on other emissions from the sector as well, mostly nitrous oxide. So let's get started. Just for context, to situate ourselves in terms of the climate impact of wastewater treatment. We're seeing sort of similar estimates according to IPCC of total emissions from the wastewater sector as we are from sort of other key targets for decarbonization. So including the chemical industry, cement, and iron and steel. So it's up there in terms of industrial polluter in terms of climate impact of sort of industrial sectors. And we know from recent work that's come out in the last several years, including some of the work I'm going to present today, that at least on-site methane emissions, particularly pertinent for Meta, are low by potentially a factor of two for our current estimates, sort of EPA's current estimates. And so really this number that we're seeing for the total climate impact from wastewater treatment could be much higher. There are over 15,000 wastewater treatment plants across the United States, and they really range in size and treatment method. And I think so you can see in this map that, the size of the dot represents sort of the flow rate. There's a wide range in terms of sort of how much waste they're treating. And sort of it's said within the wastewater industry that really, each wastewater treatment plant is unique. You have no two facilities that are the same. And kind of to underscore this point, I want to highlight a few plants. I decided to focus on California plants here. This is just to give you a sense of the different types of facilities we can see. So this is, San Francisco's Oceanside plant. This one treats about 20% of San Francisco's wastewater. It's designed to have it can treat 15 million gallons per day typically, but that can increase dramatically to 175 million gallons per day for storm events because San Francisco has a combined sewer system. So it's really affected when there are heavy rain events. Also in the Bay Area, this is East Bay Muds facility in Oakland, California. This is one of the largest wastewater treatment plants in the United States. It treats 320 million gallons per day. And then these two facilities, even though they represent sort of different treatment, approaches, you can sort of visually see the difference from them from these aerial shots. They are quite different from sort of what is actually one of the most common by number treatment approaches in the United States, which is actually a treatment lagoon. And so here's a small facility in McFarland, California, where, the waste is added to the lagoon, and this is largely natural processes that are used for treatment. So very different from these sort of bigger industrial urban facilities. So mitigating emissions from wastewater treatment, it really is a challenge in addition to the variability that you see across the different facilities. There are a couple of other factors that we want to consider. Wastewater treatment produces multiple greenhouse gases, so I'll be mostly focusing on methane today. But we also see emissions of nitrous oxide and as well as carbon dioxide, which is relevant because some of that is of fossil origin. Emissions come from both sort of point sources as well as large areas, which poses an additional challenge. And a lot of these are biologically mediated processes, which means that we see sort of inherent variability as across different treatment configurations that are designed for different biological treatment processes. And we have different microbial communities that contribute to the emissions. that are produced. But I think wastewater treatment is also it's also a promising starting point for thinking about reducing emissions, and what we learn from wastewater treatment really can translate to other sectors. Compared to other emission sources, for example, agriculture, we had a meta talk several weeks ago about livestock emissions. Sort of compare, in contrast, wastewater treatment really is a more highly controlled and engineered system with it, does present some opportunities for to facilitate emissions reduction. Especially at the larger plants, you'll have on-site personnel who are already regularly monitoring several parameters to ensure the wastewater treatment plant is operating and meeting treatment requirements. And so if we can sort of figure out how parameters that we're already measuring can correlate with emissions, that would really sort of allow us to better understand what's happening and how we can reduce emissions. So for today's talk, I'll start with just an overview of methane production at wastewater treatment. Then I'm going to discuss, as I said, sort of the modeling work that I've done at LBL, looking at our estimate for nationwide emissions from this sector. And end with sort of thinking about how we can use some of the new technologies for measuring methane in the wastewater sector. And so that's bringing some of the previous work that I did at Stanford, sort of with the controlled releases. And I think that the meta audience may be largely familiar with. So thinking about how we can apply that to this sector. So to sort of begin with methane production from the wastewater treatment sector. So the greenhouse gases in wastewater treatment are largely biologically produced for the most part. And so, we are concerned both with methane as well as with nitrous oxide. And I don't sort of expect you to internalize all the details of this slide, but sort of on the left half of the slide, we have a simplified version of how methane is produced in wastewater treatment. We are breaking down complex organics in order to stabilize them. So that way, they aren't polluting our water bodies that we discharge the waste in. And so this process sort of involves first sort of breaking complex organics into simpler organic compounds, so organic acids. And then these are in turn transformed into methane. So this process is methanogenesis. It happens when you have sort of the lack of oxygen. These are anaerobic processes. The nitrogen cycle, I'll just touch on it briefly, again, because nitrous oxide is, an important greenhouse gas that's produced at wastewater treatment. The nitrogen cycle is incredibly complicated. It involves many different types of microorganisms that transform nitrogen through many different stages. But basically in wastewater, our influent is ammonia, and our goal is to transform it either into nitrate or to nitrogen gas. And that depends on the treatment requirements of the plant itself. But importantly, sort of if you look at this schematic, there are several points in this pathway where nitrous oxide can be produced. And so depending on the balance of the microbial community, you can end up with more or less nitrous oxide production. So across the way, there are several steps involved in wastewater treatment that produce both methane and nitrous oxide. And so here for each step, and I'll walk you through these momentarily in more detail, but you can see we have different levels of production. Note the log scale on the y-axis. And this is work that came out of Princeton recently. They've done sort of a lot of work in this area, Jason Wren's group. And so we're seeing sort of not only multiple greenhouse gases being produced, but that this is really, we're going to tackle these in different ways depending on what stage of the plant it's from. So I'll walk you through a little bit more in more detail what this looks like. So we can see methane production from sewer systems. So again, the sort of lighter gray bars was methane, and the darker ones was that's sort of nitrous oxide. And so here, as we're transporting waste to the treatment plant, you can have sort of settling and sort of solids accumulating in the pipe, and this can result in methanogenesis, producing methane, which either can be sort of diffuse upward from the sewer system, or it can remain in the aqueous phase and may be produced in the sewer system, but released sort of at the treatment plant itself. Sort of the first step that you'll see in wastewater treatment plant typically is what's called primary treatment. And so here the goal is to remove large solids from your water through gravity settling. And so this process, you end up collecting your solids to send to solids treatment, and this is a process that can then produce methane. Next, the liquid that has gone through primary treatment will go towards what's called secondary treatment. And the goal here is to remove the dissolved organics. So we previously removed the particles, now we're removing sort of the aqueous phase dissolved organic compounds. And this is achieved through basically the sort of conventional approach is to pump a lot of air and mix your wastewater and to accelerate biological treatments or biological processes that would happen anyway if you were to just discharge your waste directly into a river or a stream. So have those same biological processes occur in a controlled environment. This system can also be designed, so this is traditionally designed for removing organics, but it can also be designed to remove nutrients, so nitrogen and phosphorus. And this is actually sort of will involve often a combination of both aeration and non-aeration. So here's a wastewater treatment plant. This is a photo I took recently at the Iowa City wastewater treatment plant where, they have this system for secondary treatment where there's one lane is aerated and then the lane next to it is not aerated. And that's in order to remove nitrogen. But this sort of cycling can also result in the production of a lot of nitrous oxide. And so again, if we look back at that sort of figure from the Song et al. Paper, we see that sort of measurements that have been conducted so far, looking at secondary treatment, we see higher nitrous oxide, a higher sort of climate impact from nitrous oxide compared to methane from this process. Although methane is produced, even though this is often an aerated process. So after sort of secondary treatment, the next thing to consider is solids treatment. So what is happening to those solids that we've removed, both through settling and sort of in the secondary treatment process. And so here, the goal is really to stabilize the solids and allow for them to be safely disposed. And this, I think many people that sort of are in the methane world are very familiar with anaerobic digestion, where you end up seeing a huge amount of methane being produced. And so this is sort of based on our current understanding, and this makes sense. We're seeing very high methane emissions from facilities that have anaerobic digesters. So that's that 300 grams of CO2 per meter cubed treated. And so, yeah, here's just some photos. We want to consider, of course, any leaks that would be coming from anaerobic digesters and emissions from the digestion process itself. But there's also, solids are stored on site, and there's a lot of solids handling processes that can also contribute to methane emissions as well. And of course, a lot of facilities, and I'll talk about this in a little bit more detail later in the talk, but they may have anaerobic digestion, but not use the biogas that's produced for electricity, and they'll just for electricity generation, and they'll flare. And so, here's the flare at this facility. And just to give you a little sense of what some of these emissions look like, these photos are courtesy of Trung Lee from Brown and Caldwell, who's they've been traveling all over the country taking photos of different, with infrared cameras of different methane leaks at facilities, helping them identify sort of where their methane leaks are. And so you can see this is a leak, a methane leak at the top of an anaerobic digester. Perhaps this is, an area we'd expect to see a leak, but also, as I mentioned, just in the handling of the solids, we're seeing methane leaks as well. So here, if you see where my cursor is, that you can see sort of the plume coming out of just the treated solids that are being transported for storage, likely. So just to take a step back, this is like we have several different treatment processes throughout wastewater treatment, and we're seeing different greenhouse gases being produced at different stages. But really, we need to sort of consider many different aspects of this highly complex system when we're thinking about reducing the climate impact of wastewater treatment. So with that overview, this brings me to sort of the next main portion of my talk where I'm going to be discussing work that I did at LBL, looking basically at benchmarking and creating an inventory of greenhouse gas emissions from the wastewater treatment sector. And this was work that I worked closely with PhD student Jinan Fang, who is at University of Illinois Urbana-Champaign. So in order to basically answer the question, what is the climate impact of the wastewater treatment sector, we generated an inventory of all of the facilities across the United States. So this is 15,876 different facilities. And for each facility, we sort of compiled and developed a model for the treatment train configuration. So what are the processes involved in treatment? How much biogas is being produced, how much solids are being produced, and how are the solids being disposed of. We calculated emissions for each facility using emissions factors that were specific to the treatment processes that were present. And we included not just the emissions from on-site biological treatment, but also we accounted for emissions associated with upstream energy and chemical consumption, as well as downstream emissions. So what are the emissions when you dispose of your solids offsite? And those applications typically are either for agriculture, using solids as a soil amendment, or disposing of them in a landfill. So this is a sort of schematic showing our data analysis pipeline. I'm happy to go into sort of more details on this in the Q&A, but I'll just, highlight that this involved compiling several national databases on wastewater treatment that are publicly available. This often involved a huge, huge amount of data cleaning. I worked really closely with Abby Hodson at LBL on this. If anyone is interested in working with some of these databases, happy to sort of talk through that because they are working with them and sort of understanding them is kind of non-trivial. And then so we compiled data sets on sort of what is the infrastructure that exists in the United States and also used literature values to have emissions factors for different configurations, and ultimately compiled a final greenhouse gas emissions inventory. Since I spent sort of the first portion of this talk sort of walking you through the different treatment processes, I'll just go into a little bit more detail on how we assigned treatment configurations for each of the 15,000 facilities in our database. So this is the basic schematic that we used in order to sort of a basic schematic we used for the wastewater treatment process for each facility. So these processes many of them could either be present or absent, but we basically included for every facility some form of liquids treatment in combination with some form of solids treatment. In terms of liquid treatment, we could have sort of the primary clarifier. So that's, do we have primary treatment, that first settling process that I talked you through earlier. And then we coupled this with some sort of main biological reactor for secondary treatment. So for those of you who are more into the details of wastewater treatment, we considered sort of conventional activated sludge systems, as well as aerating with pure oxygen. And then we considered different biosystems designed for nutrient removal. So removing nitrogen and phosphorus. And then we also included a trickling filter configuration, which I didn't talk about earlier, but it's sort of basically running the wastewater through sort of a fixed bed that has biological attached growth on the filter. So we also included the option for chemical phosphorus removal, and then included sort of final stages of disinfection before discharge. So for each facility also, we had these different treatment objectives. So the plant could have been designed to remove organics, as well as different nutrient removal configurations. On the solid side of the treatment, basically the main thing that we toggled here was how are we stabilizing our solids? So here we considered different scenarios for anaerobic digestion as well as aerobic digestion, multiple approaches for incineration, as well as lime stabilization. And then we considered two different ways that facilities could dispose of our solids. They either sent it to a landfill or applied it to agriculture. So for every single one of the facilities that we had, we applied sort of a configuration based on this schematic, and we ultimately had 49 different possible configurations. So here, this just sort of shows the distribution that we found across the United States of different treatment configurations. Each configuration has this sort of alphanumeric code. I'm not going to sort of go into the details of that now, but I'll just sort of talk you through a little bit of what we saw. Sort of basic activated sludge, where we have that secondary treatment that we're pumping with air, accounts for about 30% of the facilities in the United States, treating also about 30% of the total annual flow in the US. Interestingly, lagoons, we found there were 8,000 wastewater treatment plants in the US that use lagoons as some form of treatment. On the solid side, about 30% of facilities used aerobic digestion, and then a smaller number used anaerobic digestion, about 20%. But the facilities that used anaerobic digestion, they treated about 64% of total flow. So we're seeing, a smaller number of anaerobic digesters, but they tend to be sort of much larger facilities, which is, of course, meaningful for our methane emissions. Also, while we had sort of 20% of facilities in the US use anaerobic digestion, only 321 of them recover energy from the biogas that they produce. So that means a lot of facilities are flaring their gas. So in terms of estimating the total emissions from each of those configurations that we assigned to our treatment plants. So again, we considered upstream emissions. So this was the energy requirements for the plant. We applied process models for each of those configurations to have an energy estimate, and then calculated the climate impact based on the grid serving the plant, the state grid. We considered chemical inputs. In terms of on-site productions, of course, we considered methane that was produced both in anaerobic digesters, as well as from lagoons that were anaerobic or facultative, which means it was a mix of anaerobic and aerobic. We included carbon dioxide, assuming that a fraction of our incoming carbon to the plant is of fossil origin. And then we also, of course, considered nitrous oxide emissions based on the different nutrient removal configurations. So whether the plant was designed to transform ammonia fully to nitrogen gas or to nitrate, or if it was not designed to remove nitrogen at all. And then sort of in terms of downstream emissions, if the biosolids were sent to a landfill, we accounted for methane produced at the landfill. And then if it was sent to agriculture to be applied to agricultural soils, we accounted for nitrous oxide emissions from that process. So for every different treatment configuration that we included in our study, we were able to come up with an estimate for how many kilograms of CO2 equivalents are released per meter cube of treated wastewater. And so that's kind of what this shows. And you can see how for the different treatment configurations, for some methane is a greater proportion of emissions. For some, nitrous oxide is. The yellow bars are electricity, and those two configurations with the really big yellow bars, those were membrane bioreactors. So they use a lot of energy for the membrane-based processes. So once we had sort of the estimates for emissions from every single facility, we can say what is the nationwide impact. And we found our estimate of nationwide impact of greenhouse gas emissions is 27% higher than EPA's current estimate. This is largely because we found that our estimate, so there were a couple of reasons behind this. We found that methane emissions were on the whole higher than EPA's estimate, and we also did include electricity as well, which EPA did not. So yeah, again, here you can see our on-site biological treatment processes are really methane and nitrous oxide are main contributors to the overall nationwide climate impact of wastewater treatment. Electricity that is used to power the processes on the plant is also about a quarter of the total climate impact. And then a smaller portion is associated with the downstream emissions. And looking at our overall facilities across the country, perhaps unsurprisingly, we really found that most of the emissions are coming from the very large facilities. So 80% of emissions are coming from 8% of facilities. To look a little bit more closely at methane emissions. So again, that was, about 20%, 45% of the climate impact of wastewater treatment. So again, I think really an important contributor. 85% of that methane was emitted from facilities with anaerobic digesters. So we accounted for the methane emission, the methane that's produced at facilities without anaerobic digesters, but really anaerobic digesters are the heavy lifters here in terms of contributing to methane leaks. And as I mentioned before, a lot of times, really for the vast majority of facilities, we're seeing that they have anaerobic digestion, but are not using electricity from the biogas that they're producing. However, our analysis shows that the savings in terms of climate impact from using the energy produced by anaerobic digestion does not offset the climate impact of leaked methane, which I think really underscores the importance of implementing leak detection measures for wastewater treatment plants so we can find and fix those methane leaks. We also looked at sort of the geographic distribution of the facilities in our analysis. So here you can see these are all the facilities in the US with anaerobic digestion in this sort of pink magenta color. Really across the country, we're seeing, and very large facilities as well, but there is some clustering, which could be promising if we think about sort of different ways we could consider detecting these leaks or monitoring them. Our most climate intensive treatment configuration was when we had the combination of nitrifying treatment with anaerobic digestion. So that meant for our liquids treatment, we were treating to transform ammonia to nitrate, and that resulted in a lot of nitrous oxide production, and coupling that with anaerobic digestion for methane. We're seeing the double hit from both of those treatment from both of those greenhouse gases. And then finally, I want to just emphasize that with wastewater treatment lagoons, these were the most common treatment method across the country. As I said before, we saw about 8,000 wastewater treatment plants that use lagoons as their method of treatment. And these are incredibly understudied. We ended up having to rely on IPCC's emissions factors for lagoons. And really, there is not, I think, a lot of data currently available. So while these treat a smaller percentage of flow and don't contribute as much to emissions as the larger facilities do, these are tend to be, less controlled environments. You may sort of have a facility dumping their sort of waste into a lagoon and leaving it sitting, and it's not properly mixed, and so you could see perhaps a lot of methane being produced in that way. So I think this is really an area that um, um, not to be overlooked, but I think also underscores the broader point that we really do, we're limited in this analysis by the availability of measurements. And we really do need measurement data that reflects the broad configuration of wastewater treatment plants that we have, both in terms of the variability in geography, treatment process, and size. So I think, we really need to consider how we can improve measurements, both in order to have better estimates of nationwide emissions, but also in order to find and fix leaks and reduce emissions overall. So this brings me to sort of thinking about how we might want to apply some sort of the new measurement technologies that are now being used increasingly in the oil and gas space. How relevant are these to the wastewater treatment sector? So again, just, this maybe is a bit more familiar territory for a lot of the meta audience. And we're coming back to the work that I did at Stanford. But, we can think about how we might deploy different new technologies, such as like on-site ground sensors or conducting aerial surveys and satellites in order to better understand emissions from wastewater treatment. And I think that, all the advantages that you see in the oil and gas sector that these technologies provide really, really do translate, to wastewater treatment, as they would allow us to really have a better snapshot of how emissions vary both across facility, if you conduct an aerial survey of, a large geographic area, or if we can have a better understanding of how emissions are changing over time. So flashback to remember our Stanford controlled release tests for regular meta attendees. This is something that, I think you have seen many times before. Richard and I and Evan have all presented our work conducting independent validation of airplanes, satellites, and ground sensors. But for those who are sort of less familiar, just, brief highlight in terms of the quantification capabilities of these technologies. The work that we did in our controlled release testing in 2022 with the airplanes. So that's sort of this figure on the left. We found really strong quantification capabilities in the airplanes that we tested. This was just one of the 5 platforms included in that paper. We also see, slightly more scatter and lower and sort of higher limit on detection, right? With the satellites, this was Evan's work. Satellites are not going to be able to see methane emissions through, they're measuring through the atmospheric column. They won't be able to see sort of as small emissions as the airplanes were able to. But on the whole, we're seeing sort of strong trends in the right direction, like in aggregate across all satellites, we're seeing accurate measurements. And then the work that Richard and I did evaluating the ground sensors, this is an area where I think we really need to see some growth in terms of performance and more R&D in order to improve quantification so that as currently we're seeing sort of strong underestimates. So will these technologies be able to see emissions from wastewater treatment? This is work from Carbon Mapper. This was their paper where they took images from that they collected with their aircraft platform and then attempted to sort of predict if their satellite would be able to see emissions. And so they highlight in this paper by Ayasi et al. 2019, their airplane was able to see emissions from a wastewater treatment plant. This is actually a treatment plant in San Jose. And they also saw emissions from manure lagoons and dairy digesters, which were larger. They estimate that the manure lagoon and dairy digester were about twice the size of the wastewater treatment plant leak that they saw. And, I think that, while these are from the agricultural sector, we do really see lagoons and dairy digesters. These are the same technologies we're going to see at wastewater treatment plants. And so we are seeing emissions using these existing platforms from wastewater treatment or similar systems. And I've actually sort of been to workshops where we sort of looked through the Carbon Mapper platform and were able to find for, a specific wastewater treatment plant, able to see sort of the leaks coming from it, which was quite cool. So depending, I think, on the instrument, whether we're talking about an airplane or a satellite, we may be able to see moderate to large wastewater treatment plant emissions. I think it would be much more challenging with the satellites, but perhaps with the more targeted ones. Again, ground sensors, this is it seems like it would be a natural fit for the wastewater treatment sector. We already are monitoring a lot of parameters on site, and to be able to sort of add and deploy sensors around your equipment seems like it would be an ideal application, but unfortunately, we're not really at the stage where these technologies are ready to be used. And the performance that we found for the ground sensors was on a really clean background, and wastewater treatment is a much more complicated environment where there are going to be different infrastructure, buildings, infrastructure that's going to sort of obstruct plume development that would affect sort of how the ground sensors are able to estimate ultimately what the emission size is. But I think also, we've done sort of controlled release testing, as I said, on this very clean background so far, and it would be really valuable to have additional technology validation that mimics wastewater treatment plant emissions. And there are several technical challenges to sort of monitoring wastewater treatment plant emissions. This is, again, sort of circling back to what I discussed before at the top of the talk, but we see, right, non-point source emissions in addition to point source emissions. And so up until now, the technology validation has focused on single point source emissions that would be representative, for example, of a flare or perhaps a leak at the top of a digester. But we really want to see how these technologies perform across a range of different emissions conditions that we see in wastewater treatment. Emissions can also be lower concentration, which poses a challenge to measurement. On-site infrastructure can obstruct plume development and transport, again, particularly a challenge for the ground-based measurement technologies. So ground sensors also for vehicle measurements. And then perhaps, this isn't the same challenge you have with like offshore emissions in the oil and gas space, but for imaging technologies, there is the challenge of measuring methane over water. And so if you are considering sort of a very large lagoon, say, for example, for treatment, that could pose an additional challenge. All right, so this brings me kind of to an end of my talk. Just as a recap, today we went over methane production from wastewater treatment. I discussed the work that I've done at LBL, modeling nationwide emissions from this sector, and then lastly, sort of ending by thinking about how we can bring sort of some of the measurement lessons that we're learning in the oil and gas space over to the wastewater treatment sector. And I would like to give a huge thank you to my collaborators and my funding sources for the work that I shared with you all today. So thank you very much. And yeah, I guess we can stop the recording, and I'm happy to take questions.